Hey guys, hope all of us are doing fine. My name is Ernest and I'd like to welcome each and every one of us to our discussion for today. And we're going to look at the concept of a row-reduced echelon matrix. And this is going to be a form of matrix whose entries are going to be characteristic in a way that we are going to be, of course, defining in this specific video. Now, in a sense, we're going to look at the concept of a echelon matrix, which in some way we have already mentioned in some of our videos, but I'm going to combine that one, the concept of an echelon matrix, of course, in defining a row-reduced form of echelon matrix. Now we're going to consider these matrices which I've just given on the board, which is going to consist a range of values for the, or rather the range of values for the number of columns and rows. And we'll consider how we can, of course, identify some of the aspects of these specific matrices which have just, of course, defined. Then thereafter, we shall look at a procedure of finding this row-reduced echelon matrix, which is going to be forming our wrap-up of this specific video. Now, matrix is going to be defined as a matrix, a matrix that is in echelon form if the number of zeros that are preceding the first non-zero entry of a row is going to be increasing row by row until only we are left with the zero rows. And of course, we're going to see that some of the matrices which we have given on the board, of course, are going to be consisting of this specific characteristic. Now, in a sense, I've said that if we are going to consider various rows of matrices, we're going to see that for A, this is going to constitute over 4 rows, 3 rows, 4 and 4 rows respectively. Now, therefore, each of the non-zero entry, which is going to be, of course, identified as the first element of a row, is going to be regarded as the leading entry. Now, for A, we are going to identify 1 as the first leading entry from the left of this specific set of matrices for the first row and 4 for the second row, respectively. Now, in this case, I'm going to just be looking at these specific entries. Now, for the first row, we are going to have this one, and this one. And then for the third case for C, so this is going to be for B. For the third case for C, we are going to have this one as the leading entry for the first row, second row, third row, and then the rest is going to be a 0 row given as such. And for the second, for the third case, fourth case, sorry for that, this is going to be forming a matrix for D. The leading entry for the first row is going to be a non-zero given as 1, of course, 1, then 2, and the last fourth row is going to be consisting of zeros. Now, in this particular case, the letters which have been encircled are going to constitute what we refer to as the leading entries of these specific rows, and they're going to be the leftmost non-zero entries in a non-zero row of an echelon matrix. Now, in a sense, we have decided that we're going to, of course, identify an echelon matrix whereby we're going to see that there's going to be a specific sequence in which we are going to follow, in a sense that this echelon matrix form are going to be formed by numbers of zeros preceding the first, of course, non-zero entry for a row, which are going to increase row by row until only the zeros rows are going to be left. Now, in a sense, we are going to see that that specific characteristic is going to be lacking for this option number B, or a matrix number B. And therefore, we are going to be ruling out this specific matrix. Since, as we can see, for the second row and the third row, there's not going to be an increase in this specific set of row by row of these non-zero entries which we have mentioned. Since for the second and the third row, they are going to be consistent, which is going to be the same number. And therefore, we are going to monitor A, C, and D, whereby we're going to see that for each leading entry, there's an increase in this specific range of values, which you have, of course, identified row by row until we're going to be left by this 0, of course, rows, which are going to be given as such. And this is going to be the sequence for which we are going to use, of course, in trying to identify what we refer to as echelon forms or echelon matrices. Therefore, for A, C, and D, these are going to be forming what we refer to as echelon matrices. And of course, we are going to see that then therefore that we can identify a matrix that is not in echelon form, which is going to be violating this basic law of zeros that are preceding the first non-zero entry of a row, which are going to be, of course, not increasing as we have just mentioned. Now, in a sense, we're going to look at a specific type of a matrix, which is referred to as a row-reduced echelon matrix. And this is going to be assisting us in trying to of course, come up with a procedure of transforming a matrix from a matrix to a row-reduced echelon form, which is, of course, going to be assisting us in trying to do some of the evaluation, like finding solutions of our linear equations. So in a sense, I'm going to be looking at these specific procedures, and we're going to consider a specific matrix which is going to be, of course, of our interest for us to reduce to echelon or row reduced echelon form. Now, for a matrix to be echelon matrix, is going to be called a row reduced echelon matrix if it's going to be meeting the following conditions. So we're going to set a range of requirements which are going to be met for a row reduced echelon matrix, and these are going to constitute a range of requirements which we are going to list in terms of a summary form on the board. So for a matrix to be given as a row reduced echelon matrix, the leading entries in each non-zero row must be 1. So I've identified the leading entries from the previous of course matrices which I've given. So the leading entries of this in each non-zero row, the leading entries of the leading entries, we're going to put this one in summary form. The leading entries in each non-zero row. So I've mentioned the last two rows for A, C, and D were 0. So the leading entries in each non-zero row is specifically going to be given in terms of 1. And then we're going to see that procedure or consideration number 2 is that each leading one is going to be the only non-zero entry in each column. So we're going to find that each leading non-zero entry or leading one is the only non-zero entry in this specific column. So we can just give it as in this column given as such. So in that particular column that we're going to consider leading entry, then this is going to be the only non-zero entry in that specific column. And then we're going to look at another case whereby we are going to see that these are some of the fundamental, of course, aspects which we are going to consider. And in a sense, we are going to look at, of course, some of the procedure which we are going to use in trying to make a row reduced echelon or form a matrix which is going to be in echelon form, be a row reduced echelon form, which basically is going to be consisting of these specific leading entries given as 1, and of course each leading entry in each row is going to be the only non-zero entry given as such. So this specific procedure is going to constitute what we refer to as elementary row operations, which are going to assist us in trying to, of course, reduce an echelon matrix to a row reduced echelon form. So these are going to be elementary row operations which are going to be assisting us. So basically, these are going to be some of the operations which we are going to involve in trying to ensure that we comply with the first two, of course, aspect of a row reduced echelon form. So this is going to be in a set of perhaps 3, of course, a set of laws. Now that we have described what basically a row reduced echelon form is, we are going to look at some of the procedure which we can use in trying to obtain this specific row reduced echelon form. So the first one is a row reduced echelon form can be achieved by interchanging the ith row and the jth column. So we can perform this one by interchange of the ith row and the jth column. So this is legible, this column. So we are going also to look at another procedure which we can use to obtain this specific result by a multiplication of the ith row by a non-zero scalar factor. So we're going to see that we can multiply the ith row by a non-zero scalar factor. So this one we can give in terms of perhaps just a representation. So if we have an ith row given as such, we're going to perform a multiplication by an ith row by a scalar factor, where case a scalar factor that is of course not equivalent to 0, just as we have mentioned. So this is going to be a condition which is going to assist us in trying to achieve that row reduced echelon form. And of course we are going to either add a scalar multiple of a row j to or ith row to a jth column. So we can as well, of course, add a scalar multiple of row j to row I. So in this case, we can perform a specific addition of a scalar multiple of one row against another and try to see what some of the results we're going to come across. So in a sense, we can see that we are going to perform a range of operations whereby if we want to obtain a specific transformation, perhaps we can combine by an idea 1 and 2 and come up with a scalar multiplication of a particular row, and of course that can be done in combination with this specific another scalar which is going to be a multiple with another row which is going to be given as a j. And as we said, of course, this range of k and k prime are not going to be equivalent to 0 for us to achieve that one. So I'm going to give a specific example which we are going to use in trying to obtain this aspect of a row reduced echelon form, and try to see what are some of the results which we are going to obtain from this specific, of course, operation. So in this specific operation, I've just done a summary of basically the various steps which we have just referred to as elementary row operations, and I'm going to elaborate on this specific, of course, a form which we have discussed. So in a sense, we're going to see that if we have a matrix A which is going to be given in terms of this particular representation, this matrix is not first in a echelon form, and therefore we are going to be having a specific sequence of course, steps which are going to be assisting us in trying to reduce it to echelon form. And therefore, we are going to see that this specific matrix can be given in terms of a various range of operations which we have just given us a transformation of rows from row 1 to row 4. And the first case, we're going to look at a transformation whereby we're going to maintain one which is going to be having a leading entry of 1 given as such. So we're going to perform subsequent, of course, transformations for row 2, 3, and 4 given as such. So in this case, we are going to have row 2 transformed as row 2 minus, this is going to be a scalar multiple of row 1, whereby we're going to have row 2 minus 2 times row 1. So this basically implies that if we're going to have row 2 given as 2 minus 2 times row 1, so this is 2 minus 1 times 2, which is equivalent to 0. And then we're going to have 1 minus 2 times row 1 is going to be 1 minus 4, which is minus 3. And then we're going to have the next, of course, given in terms of 2 minus 2 times row 1, this is going to be 2 minus 6, which is minus 4. And then we're going to have 0, which is 0 minus 2 times row 1, which is going to be negative 2. So we're going to perform a range of operations for the subsequent rows. For instance, if we take a row 4, this is going to be a row 4, which is a 1 minus row 1, which is 1 minus 1, which is going to be giving us 0. So we are going to take this series of steps for row 2, 3, and 4, of course, and obtain the various range of values for the rows, which are going to be 0, 0, 0, and this one. So as well, we're going to see that in this case, this is going to be not in echelon form, since the leading entries still are going to be having these specific values for especially the second and the fourth row. So we're going to perform a subsequent operation, especially for the fourth row, for us to obtain an echelon form, or a form which can be reduced to an echelon form, by having a row 4 of this specific matrix minus a row 2. So this basically is equivalent to this specific row minus row 2. So 0 minus 0 is going to be giving us, for these specific values of row 4, giving us 0. Negative 3 minus minus 3 is going to be giving us 0 for 3 plus 2, 3 plus, negative 3 plus 3. And then we're going to have a 0 minus minus 4 is equivalent to positive 4. 2 minus, of course, minus 2, that's 2 plus 2 is equivalent to 4. So we can transform still this one, since it's going to be having the leading entries of this one and this one not reducing. So by transforming still a row 4 by having a row 4 minus 2 times row 2, this is going to be equivalent to the 0 row for the last one, which is going to be given as such. So in this specific case, we will have reduced this particular matrix to an echelon form. And in our subsequent video, we're going to look at an example of how we can transform this specific matrix to a row-reduced echelon form, which is going to be forming a second part of this specific discussion. And that's going to be assisting us try to identify various range of ways in which we can, of course, reduce this one to echelon, row-reduced echelon form. So kindly check our description boxes for various links of other videos. Engage us in the comment section and also ring that notification bell for different updates on our uploads that we do in math and sciences. So that is it for now, guys. Bye. God bless you. Catch us in our next video.